So to start off, we'll do a really quick recap of what we talked about on Monday. Just as a refresh, because we'll be carrying on with some of these derivations so we can get ourselves to a practical form. A lot of you can work on the homework because what we're doing is more or less just a recap, a more rigorous recap, but the outcomes of our derivations I think are very well known to most everyone. But today is where we're going to basically, I think, come up with all of the last minute stuff to actually, assuming that you came into this class blind, having no idea what thermodynamics was, should have all the materials necessary to actually go about and perform these calculations. So, we derived on Monday a combined first and second law of thermodynamics that we used as a starting point for additional derivations. So this is the first and second law. Now, if you recall, what we did was to define a system, an open system, and we linked the first and second law through the heat, the Q term, and that's how we came up with this expression here. So more or less, this is always going to be valid. This expression can never be violated because you've combined the first law, which can never be violated, and the second law, which can never be violated. So this is a very useful starting point for a lot of our work that we're going to be doing. Then we also talked about some math relationships, specifically the chain rule. So for example, if we wanted to expand the internal energy, U, with respect to T and V, what we would do is if you wanted to know how much the energy changes in a system based on varying the temperature and the specific volume or the density of the fluid, we would look at how the internal energy changes specifically with respect to temperature, times by how much temperature changes, multiplied by how much the internal energy changes as a result of the volume of the system changing, times by how much the volume changes. And so you can kind of see that you could just kind of get back to the original form, right? And you would get how much change with respect to volume, how much change with respect to temperature, and that tells us the total amount of the internal energy changing. Another one we'll be using today is the triple product rule. Right, so the triple product rule is one that always takes a second for me to figure out. We're going to have three different differentials, and it's going to equal to -1, but the order of which you kind of have to puzzle together. So I always take it and just do a, what is this? That's a counterclockwise rotation. So the z goes here, this goes there, and that goes there. So that has to be dz, dx at constant y, and then rotate again, dy, dz at constant x equals -1. So these relationships are very useful because thermodynamics is a very simplified form of basically calculus, because we only have 3 possible variables for any system that we're investigating. That allows us to expand one variable with respect to 2 others. And if you want to transform from one variable system to another variable system, we can use things like the triple product rule. Now that's going to become useful because this ds term is not something that we can very easily control. So we want to get this expression to something that's more useful so we can actually calculate changes in enthalpy, internal energy, and so on and so forth. So we use the combination of the combined first and second law plus the general rule that we only have 3 variables, which limits how many or how big this expansion could be. But in any real arbitrary system, right, if I had 10 variables, I would have to list out 10 of these different things for a total differential. If you wanted to do, if it wasn't thermodynamics. Because it's thermo, we only have 2 additional variables that we have to expand upon. But basically what we did is we took the combined first and second law, expanded it very cleverly. So if we expand du with respect to, let's say, s and v, so I'll write that out here. So expand du with respect to S and V, you'll see that we can derive some clever relationships where if we follow the same form, we'll get some identities where this would be du ds at constant V, that is equal to temperature, and then du d, what are we expanding with respect to S and V, du dV at constant S is equal to negative pressure. So basically, this and this correspond to there and there. And we can play around with this quite a bit. The last thing that we talked about on Monday was derivation of Maxwell relations. So what we do in that case is we take two thermal identities and then we take the partial derivatives opposite, knowing that the order of the differentiation doesn't matter. So if we do that process here, swap the order, we would derive the Maxwell relation of dt dv at constant S, I think, is that right? Let me see. I didn't write it down. I'm trying to do it off the top of my head. Let's see. So if we rederive it, d dv at constant S of du ds at constant v, this is equal to d dt v at constant S. Yeah, I had that right, okay. And then this one would be minus here we go. And we derive one Maxwell relation. There's several more. So in your homework in the last problem, you'll have to repeat the process, but do this for Gibbs free energy as opposed to the internal energy, which we did in class. Okay, questions on the mathematics that we're dealing with right now for thermal? Yes?
So are those all for closed systems then?
These derivations are for closed. You'll have to do it for the open systems. For the open system, right, you just have to expand it with respect to M or with respect to N, and you can derive additional identities for that as well. And that'll be based on the homework. But the procedure is exactly the same. It's just a little bit trickier because you have two things being held constant. So if we were to expand this one here with respect to mass as well, we would have to have du dm, but holding T and V constant dm, for example. That would be expanding it fully with three variables, keeping track of the mass. All right, so they say fundamental variables. So the fundamental variables of different units, so the fundamental variables of the internal energy are S and V. For enthalpy, they are S and P. For Helmholtz, they are T and V. Yeah, forget the other bars. And for G, they are T and P. Now the reason for this is because it's nice and elegant when you expand them. So when we expand the internal energy with respect to the entropy and the volume, we get out these nice, elegant relationships and the thermodynamic identities, and we can derive Maxwell relations. We like Gibbs because its fundamental variables are T and P, which are the two variables that we like to control most easily in the laboratory. Right, we can control the volume, but it's much, much easier to monitor pressure just by slapping a pressure gauge on something. Measuring the density is possible, but takes a little bit more time and effort. But this does not mean that the internal energy is only a function of the entropy and the volume. It does not mean that the Gibbs free energy is only a function of the temperature and pressure. All thermodynamic functions are variables of all other thermodynamic functions. The reason why we focus in on specific functions for specific scenarios is it just so happens that those are the useful ones under those circumstances. For chemical engineers, that turns out that enthalpy and Gibbs free energy are the ones that we really like to focus on and use. Other fields may rely more heavily on the Helmholtz. For example, in polymer physics, or anything where you're dealing with condensed phase systems, where the volume change isn't really all that significant. We don't care about it. All the phase behavior is done based on the Helmholtz energy. Because why concern ourselves with the complication of the pressure changing if the volume is more or less held constant, if it's a system that doesn't expand or contract very much. So for example, let's say, just to demonstrate this fact, we already did the nice straightforward one with internal energy, where we expanded it with respect to S and V, and we derived these two thermodynamic relationships. Nice, pretty, elegant, right? du dv at constant S is equal to the negative pressure. But let's say, for example, we expanded U with respect to T and V, like we did in this example over here. T and V. So we want to see if we can come up with nice, elegant, pretty relationships for these terms. Well, the first one we have right here, du dt. We actually just define this as something else. We just call this the specific heat. We define it as du dt at constant V. And this is where we start to get into the idea that we're not learning the system, we're not learning the solution to all of our problems, we're learning the system of how to organize our problems. There's no way that we can really calculate this very easily. We just have to measure it. So in thermo, what we're trying to do is simplify these relationships to get it to the minimum number of things that we have to go and measure. Heat capacity is one of those things that we just have to go in and measure. Right, so we need this term right here. The next one is we want to look at what is du dv at constant T. Right, this is part of our expansion. So if we're changing the temperature and specific volume of our system, and we want to know how does that change our internal energy, more or less, how much work is this process going to take us by changing these two terms in a system? Right? We take an element of fluid, we want to modify its density, we want to modify its temperature, we want to calculate how the internal energy is changing. Now, if we put this into a system, right, like a piston cylinder device, this will tell us how much work we have to put onto the system, or how much heat we have to put into the system, or how much heat or work we have to extract from the system. That's where this ties back into reality. So what we're going to do, let's see. We will take our combined first and second law, du equal to T ds minus P dV. Right, now this function is true no matter what with respect to any variable. So what we'll do is we'll take this over V, holding T constant. This term goes to 1. This term right here, this ds dv at constant T, not a super useful relationship. So we'll use a Maxwell relation, which I think is the one, no, it's not this one, it's a different one on the equation sheet. This is a Maxwell relation, so if you look at your equation sheet, this is one that will have already been derived. So if we take this information, we substitute it back into this expression up here, we'll get that the simplified form, or relatively simplified form, so by expanding U with respect to changes in temperature and volume, we can do it, but it's just kind of clunky. It's not very convenient. This is something we could most certainly calculate, especially if we had an equation of state that related pressure and temperature. Take the derivative with volume being held constant, substitute it into here, and of course we could go through the exercise of calculating all these different terms. So when they say it's a fundamental variable, they're just saying those are the variables that are well behaved in that particular system. But that doesn't mean that it's the only thing that there are properties of. All right. Here's where it all comes to a point why we're wasting our time with all of this. We want to be able to get changes in entropy, internal energy, enthalpy, Helmholtz, Gibbs. We want to get all of these functions into quantities that are useful to measure in the laboratory so we can actually begin to tabulate and keep track of how much energy it takes to change internal energy, enthalpy, entropy, and all that kind of stuff. So we're going to start off with the entropy. So we're going to, and again, these are derivations that we already know the solution to, so it seems kind of like a really straightforward arbitrary path, but obviously back in the day you would have had to tinker with this a whole lot more. So the first step is we're going to expand ds with respect to temperature and specific volume. We're going to look at these two terms separately. So what we're talking about here is we're trying to derive an equation where if I know how I'm controlling my temperature or I know how I'm controlling my specific volume, I can integrate those functions to tell me what my delta S is. Right? So if we wanted to visualize this, let's take a second and visualize this. What I'm looking at is essentially the derivative of a function where it is the entropy plotted against either temperature or specific volume. In thermodynamics, entropy is a state function, so it doesn't matter the path we take. So when we apply this relationship or this equation, we're going to do it into two steps. First, we'll vary the volume, keeping the temperature constant. Second, we'll vary the temperature, keeping the volume constant. So this example here would be for one of those two steps. So entropy we know has to be concave under all circumstances. So for example, we would have a curve that would look like this. Let's say this is with respect to changing temperature. This equation would describe the slope at a particular point. If we want to know the delta S between 2 points, that is effectively just the integration. Just as a reminder of why we're wasting our time with all this funny math and trying to draw a picture behind it. So then this would be our delta S that we're trying to get at. So delta S would be equal to the integral from state 1 to state 2 of whatever our ds function is. And we could break this up into several steps. We could say this is then integral from 1 to 1a of ds, I don't know, whatever we call it, yeah, plus integral from 1a to 2 of ds, right? And this could be a constant volume step, this could be a constant temperature step. Do some of these things ring a bell for classical thermo? Breaking it up into steps and all that? Okay, good. But the problem is, we don't know how to input ds dt at constant v into our formula that we can integrate it. If you thumb through your textbook, you probably won't find a chart of this for every fluid, or a chart for this for every fluid. Right? We need to have some way to input this information into the system. So this first one is relatively straightforward. So we're looking at the first partial derivative there. We're going to just expand this with respect to the chain rule. So change in entropy with respect to temperature while holding volume constant. We can just expand this and then say this is equivalent to changing the entropy with respect to internal energy at constant volume times by changing internal energy with respect to temperature at constant volume. We're just expanding this differential using the chain rule. Change in internal energy with respect to temperature. What is this?
Heat capacity.
Sorry, what was that?
CV.
CV. This is the heat capacity. This one here, this is a thermo identity. What is this one? It's over there on that side of the board.
1 over T.
1 over T. So this term just turns into heat capacity over temperature. Now 2 is actually really easy too. Our second term, change in entropy with respect to changes in volume at constant temperature. This is a Maxwell relation. That gets us out of trouble pretty easily. So we put this all together, and we have now derived an equation that we can actually use to calculate changes in entropy. Now we can go through almost exactly the same process, but instead of expanding changes in entropy with respect to temperature and volume, we could repeat the process by expanding it with respect to temperature and pressure. And we could come up with a similar expression. So this is as a function of temperature and specific volume. This is a function of temperature and pressure. So let's ground ourselves for a moment. Let's envision that we're doing a homework problem or an exam problem. And I ask you, what is the entropy change taking water from this temperature and pressure to some other temperature and pressure? Right, we need to break it up into 2 different steps. 1, vary the temperature. 2, vary the pressure. Assuming we're dealing with an ideal gas. Ideal gases, we have tabulated values of the heat capacity. And if you go through the back of any good thermodynamic textbook, you will find that you have a function of C sub P that generally looks like this. A plus B T plus C T squared plus D T cubed. Sometimes this will be D 1 over T squared or something like that, right? I mean, maybe it's not 2, maybe it's a 1 over T cubed or something like that. Or 1 over T, something like that. We'll call it T to the X. This, truth be told, is a really terrible way to tabulate properties, the property of specific heat. But it's super convenient for one thing and one thing only. What is really convenient about a polynomial? What is one derivative you'll never forget? Right, what's the derivative of x squared? Right, it's 2x. What's the integral of 2x? X squared. Polynomials are super, super, super easy to integrate and differentiate. And that's really important because we have to constantly integrate and differentiate C sub P. So if we have a tabulated form of the heat capacity in the form of a polynomial, really convenient. Now the reason why this is a bad functional form, and we'll talk about this when we get more into stability, more in the weeds. Heat capacity can never decrease as a function of temperature. So heat capacity should always increase. Oftentimes with the polynomial, and if you actually plot out the polynomial in your book, you'll see this a lot of times. It'll go up, and then it'll creep back down a little bit. This is actually a violation of the second law of thermodynamics. And it's a sort of a violation of the core concept of what the heat capacity is. Heat capacity for a fluid will always increase as the temperature goes up. And that's because you have access to more energy modes to store the particular energy. So as you give a system more and more energy, it'll start to rotate faster. It'll start to translate faster. You give it enough energy, then the bonds will start to vibrate. And then different types of bonds will start to vibrate. So the more energy a particle has, the more ways it has to store energy. So if you keep on giving that particle more energy, there's never going to come a point where it says, oh, I can't access that energy mode anymore, right? Once you've got enough money, you can basically buy anything you want. But if you give someone more money, then they just all of a sudden can't buy something that they previously could. So we'll talk more about this when we deal with the stability criteria based on entropy, but this is actually a violation of the second law of thermodynamics. But it's really convenient, and it's really not that big of a deal. Just be aware that curvature is really important in thermodynamics. An inflection point, a maximum or minimum, a change in sign of the derivative, all of these things can be kind of really important. Okay, so do we feel pretty comfortable about this term right here, handling this one? Something that most everyone should have seen. Take the heat capacity tabulated. C sub P divided by T is then just A over T, B over T, C over T, D over T. It's a slightly different polynomial. Yeah, you've got a logarithm here that you have to deal with, but we all know how to integrate 1 over T. This one becomes simple. That's still a polynomial. That's still a polynomial. So the only complication with this, dealing with entropy, is you got to integrate the 1 over T, which turns out to be a logarithm. Let's calculate this one here. For an ideal gas, PV equals RT, please calculate for me this expression based on this equation of state, the ideal gas law. Because I need to integrate this term, but I need something of how the fluid property behaves. So please tell me what the change in pressure with respect to temperature is for an ideal gas.
R over V.
R over V, that's the one. If we didn't have an ideal gas, this expression could be potentially a lot more complicated. I don't know, those of you who remember, I don't remember the exact functional form, but the functional form of, let's say, the SRK equation of state. Right? Remember how they have that omega term in there? They've got the eccentric factor, they've got that alpha, they've got the beta. Some of those are functions of temperature, which means you've got to take the derivative of every little annoying, obnoxious term in there. Thankfully, someone's already done it. Right? So if you go online and you search enthalpy change with the SRK equation of state, someone will have a spreadsheet that automatically calculates it. Thermo is very, very easy to standardize, and you can get these tables that basically you just plug in the material property information and it does the calculation for you. So if we take this expression right here, R over V, substitute it into here and integrate it, right? We're integrating 1 over volume with R as a constant. What functional form do we get when we integrate 1 over V?
LMB.
Right, we get a natural log.
Yeah.
So when we think of our classic ideal gas relationships for changes in entropy, we get the natural log of like V2 over V1 or V1 over V2, depending on how you want to structure it. So that's where these terms come from. Only because this term is generalizable. This is applied for every fluid, even solids. Right? This is good for solids, this is good for gases, this is good for liquids. But all we need to evaluate it then is good material property information, because we really don't have a way in classical thermodynamics to calculate heat capacity. And we need a relationship between temperature, pressure, and volume, which is an equation of state. So the equation of state has all of the power and all the information we need when coupled with a few experimental measurements. So now we have the power to calculate changes in entropy. How we solve real thermodynamic problems now is then we take these changes in entropy, we plug them into an energy balance, and from there, we can then figure out how we're interacting with the world in terms of heat or Q or work, which is really what we ultimately care about. So now let's continue and do the enthalpy and internal energy. So now we can generate expressions for those terms. And it's kind of funny that when we think about dealing with thermodynamics, we would prefer never to deal with entropy. But it's actually the relationships you generate with entropy are way more elegant and straightforward than they are with internal energy and enthalpy, which is kind of ironic, I suppose. We'll start off with our combined first and second law of thermodynamics. We'll just substitute in our expression for entropy that's expanded based on T and V. The reasoning behind that is we've already got an expression right here in terms of V. So we'll write this out. There we are. That's C sub V over T. This is just ds that's expanded with respect to temperature and volume that we just derived. And when we go through and clean this expression up a little bit, we find that this is equal to C dt. Basically do exactly the same procedure for enthalpy, but instead we'll substitute in the expression for the entropy expanded with respect to temperature and pressure, because we know, just based on our previous knowledge, that enthalpy seems to work a little bit better with respect to pressure changes. So we'll use what we derived in class on Monday, the combined first and second law, but in this new form of enthalpy. Right, this expression here, we started off with the combined first and second law. We defined enthalpy as U plus PV, and then just sort of did a little bit of substitutions and mathematical simplifications, and we came up with this form right here. That's where this term comes from. This is, again, another expression of the first and second law of thermodynamics. But if we substitute everything in, the expression becomes straightforward again. Okay. These are our two big conclusions of today's class, these expressions here. Now, with Helmholtz, and Gibbs, we can effectively just calculate entropy, internal energy, or enthalpy, and we can calculate those expressions there. We don't typically worry with those. The reason why we would care about dG, or changes in Gibbs free energy, is because we're dealing with phase change operations. As it turns out, that's not a very useful form. Fugacity is a much more useful form to calculate phase change properties in the Gibbs free energy. And so that's why we don't typically see these types of relationships for Helmholtz and Gibbs. It's because there's a little bit of complexity that we'll talk about when we deal with multi-component systems, but it's actually easier to use this new concept called fugacity, which again is just a made-up quantity. It's a made-up quantity that's a mathematically convenient functional form to help us solve problems. And that's why it's more useful than these terms, and that's why we don't typically see them. All right. For ideal gases, does the internal energy or the enthalpy of an ideal gas depend on pressure and volume? So if I take an ideal gas
Temperature only.
and I keep its temperature constant and I pressurize it, does its enthalpy change? No. So, what do we suppose that this term turns into when we substitute in the ideal gas law?
V.
This whole term. Let's go through this as an exercise. So I want everyone to calculate this term, volume minus the temperature times by the partial of volume with respect to temperature at constant pressure. What does this equal to for the ideal gas law? So take a moment and we'll go step by step to demonstrate what this is equal to. And I will call on random people to force you to go through the derivation on your own. Well, we know it's 0.
Yeah.
But the process is important. Okay, G Young. How do I handle this expression here? What do I substitute in here for the V?
RT over P.
Yeah, that's it. It's very straightforward. We just rearrange the ideal gas law. Okay, minus T. Someone tell me what dV dt at constant P is. We'll go with Ashray. Which I don't. No. Oh, prane. Sorry. Sorry.
It's going to be R by P.
R by P. Well, that looks pretty dang similar. This cancels with this, and we just get a 0. And we can go through exactly the same exercise for this one here. So these terms, they're kind of, they seem very abstract and obnoxious when we talk about thermodynamics, looking at the combined first and second law here, right? But the reason why we write these as such is because they're so generalizable. We can take it with respect to anything. We can divide it by any differential we want. We can integrate, we can manipulate it, and so on. So I always like to take these moments where we pause for a second and actually plug in some real equations and look at what these actually are talking us in terms of functions. Okay, the last thing I wanted to get over today is to derive an expression of how C sub P and C sub V are related. And most of you may already know the outcome of this one. What is C sub P minus C sub V? For an ideal gas, what is this?
R.
It's just R, right? For an ideal gas, we know, or we can write C sub V is equal to C sub P minus R, or C sub P minus C sub V is equal to R. They're just related by the universal gas constant. But this is because the real answer looks something like this. And it just so happens that when we substitute in the ideal gas law, it simplifies down to just being R. But we would like to come up with the general form of it. So, how we are going to get to this. C sub P is defined as how the enthalpy changes as a function of temperature at constant pressure. from our playings around over there, we know that this is also equal to changes in entropy with respect to temperature, but times by the temperature. Same thing with C sub V, very similar relationship, except this is defined as the change in internal energy with respect to temperature when the system volume is held constant. And we can also relate it to entropy in a similar fashion as the enthalpy. So again, we're going to start off actually looking at things from the perspective of the entropy, because it just always happens to turn out that the entropy answers are always a little bit more elegant. Again, remember that we are doing these derivations with the knowledge of hindsight, so we know what the outcome is. So I'm always going to give this nice convenient derivation. So we're going to start off with actually this functional form of the entropy right here. And what we're going to do, right, this expression already has C sub V in it. We need to find a way to get the heat capacity C sub P in this expression. So we're going to use this as our gateway into the system. So we're going to take this generalizable equation. This equation holds true with any changes. Changes with time, changes with temperature, changes with pressure, changes with internal energy. Right? We don't write the denominator differential because anything we can substitute in there, this expression is still valid. So to give us a gateway into relating this to the C sub P, well, let's use this one here. Let's take this whole expression and differentiate it with respect to temperature, holding pressure constant. Right, this expression just goes to 1. We can do a little bit of arithmetic. If we times this temperature through the whole process, we will get that, let's see, here we go. C sub P is equal to C sub V, right? So this, if I times by the temperature, T ds dt, T ds dt, that's just the C sub P. Then we got rid of this, that's C sub V plus T, change in pressure. So we could stop at this point right here. The reason why we can stop at this point is because this we could get from an equation of state, and this expression here we could get from an equation of state. This is not the traditional form that we put this relationship into. We can write it in a slightly more compact way that involves a little bit of tedium in terms of the mathematics. So what we'll do is we'll manipulate this a little bit just because it's the way that it's oftentimes presented. But that expression is totally valid. We could use it. But what we're going to do real quick, just to give a little bit more play around time with some of these mathematical rules that we derived, we'll expand this expression here using the triple product rule. So if we substitute this expression into here, we get that the heat capacity is equal to C sub P equals C sub V plus T. I got rid of this one here, so this is our minus then. Minus dV, so that one's squared. Now the reason why we did this step is so we can insert these two definitions. Alpha is typically used for the coefficient of thermal expansion. Coefficient thermal expansion. which is defined as 1 over the specific volume times by how the volume changes with respect to temperature at constant pressure. So if I heat this thing up at constant pressure, let's say atmospheric pressure, this tells me how much the system would expand. The other term that's useful, kappa T, we use to denote the coefficient of isothermal compressibility. Isothermal compressibility, and again, this is defined as how the, it's defined as 1 over the specific volume by how much the system changes when I pressurize it at a constant temperature. How easily can I squeeze this system down? If it's a rock, not very much. If it's a gas, I can squeeze it. So from that, we do our substitutions, plug them into here, and we can find a relationship such that C sub P minus C sub V